Hello everyone, I'm Shaskar Datta doing CSC of SPC Bangalore, and today we are going to learn about embedded systems. So what are embedded systems basically? Embedded systems are those systems which are the combination of hardware and software and which are used to do a specific tasks. There are two types of systems. One is digital system and one is embedded system. So what are digital systems basically? Digital system that provide service as a self-contained unit, for example desktop PC, part of a larger system, for example, digital control system for manufacturing plant. And what an embedded system, part of a larger unit, provides dedicated service to that unit. Embedded systems overview. Computing systems are everywhere. Basically, you see all those kind of systems everywhere near you. Most of us think desktop or computers. So their examples are what PCs, laptops, mainframe servers. They're basically desktop computers. Embedded systems overview. Embedded system, embedded computing systems. Computing systems are embedded within electronic devices, hard to define. Any computing system other than desktop computer, billions of units produced yearly versus millions of desktop units. Perhaps hundreds for household and automobiles. Like basically these types of which are like electrical contains embedded system. Computers are in cars, chips are in cameras, even washing machine. So yeah. So in this picture you can see that in day-to-day life, embedded systems are very important in our life. So you can see the many kinds of machines and all which uses embedded systems. So you can see this picture. So next, so these are some of the short list of embedded systems. You can see these are some of the examples, but the examples continues. There are many more. Yeah, examples of embedded systems. PC having dedicated software programs and appropriate interfaces to a manufacturing assembly line. Microprocessor dedicated to control function in a computer. Example, keyboard, mouse, input control. Outline of embedded systems. Design channel, optimizing design metrics, technology, processor technologies, and design technologies. So basically, there are two types of technology, processor and design. So these are some of the application domains. Consumer products, appliances, games, AV, intelligent home devices, transformation such as autos, trains, ships, aircrafts, plant control, manufacturing, chemical, power generation, and these are some of the parts of embedded system. So the given are memory, processor, actuators, hardware unit, sensors. Yeah, what are actuators? They are the mechanical components. For example, valve sensors input data. Example, accelerometer for airbag control, data conversion, storage processing, and decision making. Range of implementation option. Single chip implementation system on a chip. Functions and design criteria of an embedded system. Monitoring and control function for the overall system. For example, vehicle control uh, and information processing functions. Example, telecommunication system, data compression, routing, etc. And criteria, performance, reliability, availability, safety, usability, etc. Some common characters of an embedded system. So it can be single function, tightly constrained, or reactive. So single function can be executes a single function executes a single program repeatedly, tightly constrained. It can be low cost. It is low. It is low cost, low power, small and fast, and etc. So it can be many more. It can have many more characteristics. Reactive and real time. Continually reacts to changes in the system's environment. Must compute certain results in real time without delay. So this is one of the basic examples of an embedded system. So this is the digital camera, and this is the uh, flowchart of how the digital camera works. So it is single function, always a digital camera, tightly constrained, low cost, low power, small and fast, reactive and real time, only to a small context. So these are the design challenge optimization. Common metrics are unit cost, the monetary cost of manufacturing each copy of the system, including NRE cost. NRE is basically non-recurring engineering cost. One-time monetary cost of designing the system. Size also matters. The physical space required by the system, performance, the execution time of throughout of the system, power, the amount of power consumed by the system, flexibility, the ability to change the functionality of the system without incurring heavy energy cost. Common metrics: time to prototype, the time needed to build a working version of the system, time to market, time required to build a system to the point that it can be released and sold to customers. Maintainability, the ability to modify the system after its initial release. Correctness, safety, and many more. These are the performance design metric of an embedded system, widely used. Measure of system widely abused. Clock frequency instructions per second, not measures. Digital camera examples are user cares about how fast it processes images, not clock speed or instructions per second. Latency is response time, time between task start and end. Example, cameras A and B process images in 0.25 seconds. Uh, throughput tasks per second. Example, camera A processes 4 images per second. Throughout throughput can be more than latency seems to imply due to concurrency. Example, camera B may process 8 images per second by capturing a image while previous image is being stored. So this is the equation. Speed up of B over S is equal to B's performance by A's performance throughout. Speed up is equal to 8 by 4, which is 2. So that's how we calculate speed up of that's how we calculate the throughput speed. Basically, there are three types of technologies which we're gonna learn here. So, what are technology basically? A manner of accomplishing a task, usually using technical processes, methods, and knowledge. So the three technologies are processor technology, IC technology, and design technology. So, what are processor technology? The architecture of the computation engine used to implement the system's desired functionality. Processor does not have to be programmable processor. Programming processor are equal to general purpose processor. So this is the flowchart which you can see. So processor variant customized for the problem at hand. There are three types of processors: general purpose processors, application specific processors, and single purpose processors. General purpose processors, programmable device used in a variety of applications, also known as microprocessors. Features: program memory, general data path with larger registered file and general ALU. User benefits: low time to market and NRE costs, high flexibility. Intel or AMD are the most well known, but there are hundreds of others. Application specific processors, programmable processors optimized for a particular class of applications having common characteristics. Compromise between general purpose and single purpose processors. Features are program memory, optimized data path, special functional units. Benefits are some flexibility, good performance, size, and power. So this is the flow chart you can see. Independence of processor technologies. Basic trade-off: general versus custom with respect to processor technology or IC technology. This is basically the third technology. The two technologies are independent. So you can see the flow chart here. Design technology: the manner in which we convert our concept of desired system functionality into an implementation. Basically, is design technology. Design productivity exponential. So here you see the bar graph. There is an exponential increase over the past few decades. The productivity. Design productivity gap. While designer productivity has grown at an immersive rate over the past decade, the rate of improvement has not kept pace with chip capacity. Chip capacity. So here you can see the bar. Here you can see the graph. 1981 trailing edge chip required 100 designer months. So this is basically an example. And 10,000 transistors strength or 100 transistors per month. But the like it is 1981 leading edge chip required 100 designer months, 10,000 transistors per 100 transistors per month. 2000 leading edge chip requires 30,000 design months, 150 million per 5,000 transistors per month. Designer costs increased from 1 million to 300 million, which is a huge gap, which is a huge, which is a huge increase. So here you can see the chart, graph, mythical man-month. The situation is even worse than productivity gap indicates. In theory, adding designers to team reduce project completion time. In reality, productivity for designers decreases due to the complexity of team management and communication. In software community known as ethical man month, at some point can actually lengthen project completion time. Too many cooks. So this graph you see, core design methodology. Design of systems involving hardware and software. Basically, it is an embedded system. Starts with formal abstract specification, series of refinements, maps to target architecture, allocation, partitioning, scheduling, communication systems, means to manage large-scale complex systems. What are complex systems? SoC, system on a chip, millions of gates on a chip, decreasing processing technologies, deep submicron, 0.5 micrometer and below, decreasing geometry size, increasing chip density. Problems are electronic design automation tools, can be said EDA, time to market. Abstraction, reduce the number of objects managed by a design task, example by grouping objects using hierarchy. Computer-aided design, CAD, for example, logic level transistors grouped into gates, register, transfer level RTL, gates grouped into register, ALUs, and other RTL components. And these are some of the examples for core design. System level processors of the shelf for application specific, memories application specific integrated circuit, ACICs, input output interfaces, etc. Integration of intellectual property IP, representations of products of the mind, use of formally designed circuits as core cells. So these are the system specification. This is the system specification. Describes the functionality of the system without specifying the implementation. Describes non-functional properties such as performance, power, cost, and other quality metrics or design constraints. May be executable to allow dynamic verification. What is allocation? Selects the type and number of components from a library and determines their interconnection. Implements functionality so as to satisfy constraints, minimize objective cost function. Result may be customization of a generic target architecture. Partitioning defines the mapping between the set of behaviors in the specification and set of allocated components in the architecture. Satisfy constraints, minimize costs, not yet near implementation. Multiple behavior in a PE. And scheduling. Interactions between P's, communication. Design model. Additional level of hierarchy. Functional equivalence with specification. Scheduling. Given set of behaviors and optionally a set of performance constraints determines the total order and time for involving behaviors running on the same PE. Maintains the partial order imposed by dependencies in the functionality. Minimizes synchronization overhead between PEs and context switching overhead within each PE. Communication synthesis implements the shared variable access between accesses between concurrent behaviors using an inter-PE communication scheme. Shared memory read or write to a shared memory address. Local PE memory send or receive message passing calls. Inserts interfaces to communication channels, local or system buses. Next is analysis and validation. validation. So they are the functional validation of design models at each step using simulation or formal verification analysis to estimate quality metrics and make design decisions. Tools are static analyzer, just program, ACIC metrics, simulator, functional, cycle-based, discrete event, debuggers, access to state of behaviors, profiler, dynamic execution information, visualizer, graphical displays of state and data. What is backend? Implementations. So these are some of the implementations for backend. Processor. Compiler translates model into machine code. ACIC high-level synthesis tool translates into netlist of RTL components. Interfaces are uh, special type of ACIC that links a PE with other components, implements the behavior of a communication channel. So yeah, basically these are the important topics we learned today from this slide. Embedded systems are everywhere, which we know from our day-to-day life. We use it everywhere. So the key challenges are optimization of design metrics. Design metrics compete with one another. Unified hardware and software is necessary to improve the productivity. Yeah. And the key technologies, what we learned, processor, you know, processors are general purpose, application specific processor, and single purpose processor. We learned about design, the compilation, synthesis, libraries, IP, test and verification. So thank you everyone. This was my video about embedded systems. Please like, share, and subscribe. Thank you.